tried to make it as general as possible. So I tried to make it for a general audience. So I apologize if it's a little too basic, or it's a little not basic enough. My topic of interest is the HIV vaccine and why we don't have one. And I call this talk a lesson from the trench. And I say that it's a lesson from the trench simply that I'm coming in from the perspective of a foot soldier, not a seasoned veteran.
Actually, move away from the speakers and speak a bit closer to the... Yeah.
Vaccines work by creating an immune memory. So you introduce your body's immune system to a vaccine for the first time. For example, for measles, mumps, and rubella, we take the virus, we attenuate it so it's not dangerous, we introduce it to you. So now when the immune system comes back and sees that it says, I've seen you before, I know that you're a bad guy, and I'm going to fight you. For something like the new HPV virus, vaccine on cervical cancer.
Just move away from the speaker. Yeah. Or speak extremely loudly without a microphone. Yeah.
You're right in front of the speaker.
Yeah.
He's an expert on sound.
Yeah.
So for something like hepatitis B, instead of using the whole virus, use proteins that the virus has. This is the virus's calling card, right? So these proteins don't change. So you inject part of the protein of peptide into you, and now when the virus comes, your immune system says, hey, I noticed that calling card, that's a bad guy, I'm bouncing out of my party. So first I thought I'd address why we don't have an HIV vaccine for purely scientific viewpoint. Okay? So here's where I try to keep it simple and general. So your immune system has two arms. One side is the T cell side, makes antibodies, and then the T cell side is the cellular side that keeps a memory for you and fights the bad guys. On the B cell side, it's pretty hard with HIV. HIV is hyper-variable. That means it changes a lot. The virus has an envelope, and on the envelope it has spikes. And these spikes would be great to target a virus to, a vaccine to, but they change all the time. So here's my analogy. You're a cop, you're the immune system, you're chasing a suspect into grand substitution. And every 5 minutes, he's changing his costume. He's like Mystique from the X-Men. He's blue, he's green, he's got a mustache on, he's got a hat. It's pretty hard to keep up with the suspect, changing super fast. So that's the analogy I make for that. From the cellular side, we need cell-mediated immunity. These are your T cells. You need something to remember that it's seen the virus before, and you need something to actually secrete chemicals to fight it and kill it. The problem with HIV is that for most of our vaccines, you get infected with a virus, and your immune system actually lets you get infected and then fights it off. Right? It's seen it, it clears it. But for HIV, there's a very small window of time to actually fight it. If you don't get it in that window of time, it establishes itself in the host reservoir. So what does that mean, right? So this is like our policy on terrorism, right? It's like, okay, we have to beef up security at the airports because that's our, like, you know, small break. And if we don't get the terrorists out of the airports with the little cameras, you know, then they're going to integrate into society and we'll never find them again. Well, with your immune system, with HIV, unfortunately, that's true. So we've had a few HIV vaccines go through efficacy trials, and the results have been a little bit disappointing. We haven't actually been able to see a reduction in the viral load, and that's a problem. What people are now studying is a population of long-term HIV-infected patients who don't progress. And these guys have a solution in their bodies. They're non-progressors. They're not on antiretroviral medicines, but they maintain stable, healthy lives despite the fact that they carry this virus, and they don't get sick from it. And we don't really understand why they don't get sick. So a bunch of smart people with a lot of money said, all right, well, let's study these people and look at all their antibodies and study all their antibodies. So we did that. We thought, well, we know what their antibodies are fighting. Maybe we can make a vaccine with that. Guess what? Their antibodies are fighting a lot of things, and it changes a lot. So this is difficult. This is a moving target, and it's probably not going to be any golden bullet. Then I thought I would tackle this problem from a non-scientific point of view, based on some of the arguments I've heard and based on some of the experience that I've had. So some of the arguments I've heard when I said, oh, I'm coming to this place, Rockefeller, they make a lot of vaccines there, they're trying to make a vaccine to HIV. Somebody said to me, but we don't need a vaccine because we have antiretrovirals. So I didn't really say this to the person, I held my tongue, but that sounded to me like Jonathan Swift, a modest proposal. Like, okay, so we're overpopulated, and there's too many children in Ireland, and they're starving, so let's eat them. Like, that's a solution. So we need a solution. We don't need a Band-Aid. Okay, myth number 2, we don't spend enough money on HIV. In 2008, our HIV spending was about $868 million. Yay, Bill and Melinda Gates. Actually, philanthropy accounted for about $100 million. And public sector was $730 million, and $33 million came from industry. And I had the great pleasure of hearing Tashi Yamada, the director of Bill and Melinda Gates' Global Initiative, speak at the Rockefeller. He was a wonderful speaker. But what I found as a junior scientist a little bit discouraging is I walked out behind these two great immunologic icons, listening to them talk, and I heard one say to the other, this guy's got it wrong. They're wasting their money here. That's not what's going to cure HIV. And that was, to me, a little disappointing. And I think that in general, philanthropy is wonderful. It's wonderful that we have funds and people who want to solve these problems. We just have to be smart all the time about how we do it. So then I thought, well, what do we need to do differently? So I thought I'd share some lessons that I've learned in the lab and in science. My first lesson is don't actually do what you do best. So I'm Asian, and I have Asian parents, and they raised me saying, do what you do best, right? Jump this hoop, do what you do best. But in fact, there's another saying in life, which is that do best what needs to be done. It's maybe not the time to actually do what needs to be best, because we do what we do best, not what's best to do. So with scientists, the more senior you are, the more likely you've gotten there by taking a particular approach and a particular strategy. And you have more, say, to lose by being wrong. And so you're more unlikely to change your course if you are wrong. But I think that for something like HIV, that could be a problem. What we need to do is get people when they're starting out and commit them to this for life. And let them make mistakes, let them be wrong, because we're not going to get it right the first time. And on being wrong, I thought I'd share my second point, which is it's okay to be wrong. And I titled this point, Play Poker Well. And I say this, I had the great privilege of working for a while in science with Gil Chu. So Gil Chu is the brother, for those of you who don't know, he's the brother of Stephen Chu, the Secretary of the Energy. So he's a smart guy too, right? So he didn't win the Nobel Prize in physics like Stephen, but he's a pretty smart guy. He's an MD PhD in oncology. And I said, Gil, how much of science is luck? How much of success in science is luck? And Gil said none. And I thought, that seems, well, maybe arrogant, except Gil's a very modest guy. So I asked other people around the lab, and I found the more junior they were, the less likely they were going to say that scientific success was not correlated with luck. Junior people said it's all luck, and senior people said it's not luck. And so I went back to Gil and I said, well, there's a confounding variable here, and that's success. People who are successful don't actually want to admit that they got there because of luck. And he said to me, the way only a wise professor could say, no, sit down. Science is like a game of poker. You're going to have good hands and you're going to have bad hands. In the course of your career, you need to know how to play both hands. And a good scientist is a scientist who knows how to play both sets of hands. So stay at the table long enough to play both the good hands and the bad hands. And that's what we need to do. We need to keep people at the table long enough to be wrong and recover from it and be right. Because if we're expecting everybody to be right and have a good hand the first time, not everybody's going to have a royal flush. Okay. My final point is to stay objective and rational. What's amazing is not actually that we don't have an HIV, but what's amazing is we have a vaccine to anything at all, right? I mean, isn't it amazing that we decided that someone noticed, like, a veterinary doctor noticed that cowpox, prevents you from getting smallpox. Hundreds of millions of people were dying of smallpox, and we've forgotten that. This was a huge epidemic. This has killed more people than we've killed in wars, and we forget about that because now we have vaccines for it. We take that for granted. Instead of going out in uncharted territory by shooting bullets in the dark, we need to actually stop and go back and understand why the vaccines that we have actually work. But it's not sexy to do that, right? Nobody wants to say, I'm going to go out and cure measles. Right? Measles has been cured. We want to say, I want to go out and cure cancer. I want to go out and cure HIV. So we need people to go back and understand how to cure the things that we need to cure. And in fact, in reality, we've already created the perfect solution. We just don't know how we did it.
We have a few minutes for questions. Does anyone have a question for Nira?
Can I ask a question?
Sure.
I mean, obviously I'm a scientist, obviously I haven't studied philosophy, but I think part of the problem with stifling innovation is the regulations that are in place, especially for medicine, like you said about smallpox. In those heydays, you basically fly by the seat of your pants, basically. You did your experiments on yourself, or you did not have to do 5, 10 years, 15 years, and spend $10 million, $billion to get a new drug out. And that's I think that the problem with our approach. And I understand it, it's for the safety. I mean, obviously thalidomide, was a classic example where a drug was rushed through and caused a horrendous lot of defects. So there's a balance to, you know, rushing drugs through and not costing billions of dollars. So, but can you see any way around it? Any way of basically, preventing the stifling of innovation, especially in medicine, but yet having, safety in place so that, you don't have like thalidomide incidents again?
Well, I apologize for speaking with my back to you first, but that's a really tough problem. I mean, what scientists and physician scientists faced in that day was very different. Now we have IRBs and INDs and safety protocols, and those are obviously in place to help protect patients, right? But that's also a problem. When we take drugs from, say, phase 2 to phase 3 clinical trial, there are going to be negative outcomes. And for us in society, negative outcomes are not well tolerated. We don't like to know that there's a slightly greater risk of death. Even if, say, as for a population of, say, 300 patients with stage 4 melanoma, who have a very short-term life expectancy already. But if we see early measures that this drug might be risky for those patients, we pull it off the market, when in fact maybe we haven't seen it out far enough to actually know if it has a good effect. It's a tough problem in medicine. I think partnerships with industry help a lot. I think there's an efficiency process in industry that can really help take things into market and into R&D a lot faster than we can necessarily in academics. I think translational programs help us do that and help young scientists, speak from the perspective of the young scientists, navigate the regulatory landscape and actually do translational science. And I think that that's kind of where the NIH is heading too. I think we're heading towards everything with a human focus, and it's difficult. There's less trial and error. There's more trial, and if there's a chance of error, let's pull it off the trial. So it takes risks. I mean, I asked, a friend who runs a company that develops cancer drugs about this, and he said, this is not a game for people without balls. Forgive the expression. And he's absolutely right. He's absolutely right. Because actually being able to take that into a patient and inject a patient with something is a very different matter.
Well,
we can't drink our H. pylori, right?
Well, I'll talk a bit later, but I don't believe industry is necessarily helping, to be honest with you. I'm in industry, but we'll talk about that a bit later. But I think that's another stifling thing to innovation, is the approach to industry these days. But like I said, I'll talk to you about that. That could be a long chat.
I'd be happy to. Happy to.
Wondering, when it comes to the efficiency of using money for research, HIV and AIDS is very different in the sense that it's preventable. Right? It's not like measles, smallpox. You just walk down the street and somebody's coughing and contract it. Okay, if you make the right choices in your lifestyle, then your chances of contracting AIDS are tiny. Is it better to spend money on education, or is it better to spend the same amount of money on researching for a vaccine?
That's a really hard question. I think that's a very, very tough question. I mean, no one would say, no, you shouldn't spend money educating people. It's just that we know that a lot of our efforts to spend money on education haven't prevented the growth and spread of this disease, particularly in countries where education efforts fail, and they often fall secondary to cultural norms and stereotypes and behaviors. So I think it's really hard. I mean, it's a hard problem, and we do have to kind of come at it at different approaches. But personally, I think, I obviously come from the point of view of thinking it's absolutely amazing and wondrous that we've gotten as far as we have with a lot of the diseases that at some point people didn't know could be eradicated. I think of a couple examples. One example that I think of is the example of, say, penicillin as a treatment for syphilis. For a long time, people were suffering with syphilis and neurosyphilis, and it's absolutely amazing that in the advent of penicillin, syphilis is largely a transmissible disease, right? This is when you could have educated about behaviors. You could have talked about prostitution, you could have talked about all kinds of things, but it wasn't stopping the spread of disease, and in fact, in recent years, we've seen a rise in syphilis. But really, what's amazing is that we have something so simple as a single shot of penicillin G that can reduce your levels of carrying the spirochete enormously, that I personally would put my faith in actually developing therapies. But maybe that's a cynical view, that I put my faith in the science and less in the people. So.
Yours wasn't a medical question, so I think your question was a sociological question.
It's a philosophic question or a policy question, yeah.
There's an amount of money available. Are you going to put it on education, birth control, condoms? Are you going to put it on research labs for a vaccine? Same dollar. Where is it going to generate more value?
I think people are more likely to get a shot than wear a condom. That's just my personal belief about society.
I was going to throw my 2 cents in. I mean, you have to consider the fact that in most of the world, that the cost of a sexual act is cheaper than a condom. In most of the third world and second world that we're dealing with, to have sex with a sex worker is less than $1, and the cost of a condom is roughly about 75 cents to $1, where you're going into these places. The question I had for you was, you brought up smallpox, right? It's just interesting because that was an exclusionary sort of treatment, whereby they literally put quarantine around people, and they put quarantine around people until they brought it down. Now you're dealing with varying levels of bug. Okay, you're dealing with the AIDS of the 80s, where people have mitigated their sexual partners, understand this, are informing their sexual partners, and aren't susceptible to what you're dealing with, which is the superbugs of today. But now what you're dealing with is also highly multivariate forms of the bug, with proteins that jump and shape and change. So, one, how are you addressing these sorts of things? And to go back to what the CDC sort of advocates, what about the whole quarantine issue?
Quarantine's tough. We're not going to quarantine people with HIV, right? I mean, if you have patients who live with HIV now and are very well controlled and survive among us and do well, and they should be members of our society, and we should embrace those people. We're not going to actually quarantine them because it's preventable, it's not transmissible, because it's not aerosolized. I mean, smallpox epidemics just spread so fast that the only solution was quarantine. So I think it's a little bit apples to oranges. You're absolutely right. HIV changes so fast, and I didn't want to get into too many scientific examples, but for example, any individual who's infected with HIV-1 has more different strains of HIV-1 within them than all of the different strains of influenza we have in this country this year. That's pretty amazing. Look how bad the flu vaccine is, right? By the time it gets to us, how effective is it, right? We vaccinate the elderly, and maybe this is also a controversial topic. We vaccinate the elderly, but their immune systems aren't necessarily going to respond well to the vaccine. It's really hard. These are really hard public health dilemmas, right? But here we have a true opportunity. We have a true opportunity because we have a really worthy opponent. We have a worthy opponent, but you know what? We've done it before, and I do believe we can do it again. But I think it's going to take really understanding why what we've done before works. I think a lot of science, a lot of medicine, getting back to your point, was empirical, and people say, okay, I'm going to drink this H. pylori, and I'm going to correlate it with ulcers. I'm going to shoot this into someone, and I'm going to see if I have a readout. And we're past that cause and effect stage of science. Science is no longer that way. Science is all mechanistic, right? Now we have antibody therapy to receptors. We have to understand the mechanism and target the mechanism and really understand that well. Our science has evolved a lot, our approach has evolved a lot, and our understanding of how our vaccines work has to evolve with that. We have to go back and ask the hard questions about the things we've already cured. We have to really understand how we've made that happen, and then only, I think, are we going to know how to make this happen.
One last thing, just one last thing. I laud you in your statement on luck. I really laud you, because it's not all pure science. Sometimes these things just sort of pop up.
Yeah, that was awesome.
Thank you.